Welcome. In this lecture, we study what is a homomorphism and isomorphism of groups. So what is the definition of homomorphism of groups and isomorphism of groups? So homomorphism of groups. So what is the definition of homomorphism of groups? Okay. So a mapping F from group G to group G dash is said to be homomorphism of G into G dash if f of A into B is equal to fa into f of B for all AB belongs to GL. So here G and G dash we need to group. Then the mapping F from G to G dash. So what is the mapping here? So F from G to G dash. G to G dash is said to be homomorphism. So the function F is said to be homomorphism if F of A into B is equal to FA into FB. For all AB belongs to G, then the function F is said to be homomorphism from G to G dash. So this definition is very simple. So we take an example and understood better the definition. Okay. So then what is the isomorphism of group? Isomorphism of groups. Okay. So this is also definition, a very simple definition. A mapping F from group G to G dash is said to be isomorphism of G into G dash if 1. What is 1? So F is a homomorphism function. To define isomorphism of a group of the function F from G to G dash, group G to G dash, then what is the first condition? The first condition is F of AB, A into B, is equal to F of A into F of B, means what F? F is homomorphism. It must be homomorphism. Then the function is isomorphism. Homomorphism. So what is the next condition? So next condition is F is one-to-one function. One-to-one function. So what is one-to-one function? So means distinct elements have distinct images. Okay, distinct elements have distinct images. So that is function is 1 1. Distinct images. Okay. Then third is what? F is onto. F is onto. A mapping F from group G to G dash is said to be isomorphism of G into G dash if F is homomorphism, F is one-to-one function, and F is onto function. Okay. So what is the one-to-one? So we revise. So what is, you know what is a homomorphism, but what is a one-to-one function and what is a onto function? So for example here, so that is a G and G dash be the group here. G and G dash be group. So that is A and B are the two distinct elements from set G. So we map. There is a mapping F from G to G dash. So we get elements F of A. Also mapping this. So we get F of B. If F of A and F of B are distinct elements, then we get A and B are also distinct elements. So these are the elements in G dash and G dash, and these are elements in G here. Means what is this? F is 1 to 1 means what here? So F of B is equal to F of A implies that A is equal to B. Okay? Then the F is, so what is the definition of 1-to-1 function? So that is F of B is equal to F of A implies that A is equal to B. Okay? So means what is the meaning of that is this. So A and F, these are the different, then this element also different. If these are elements are same, then this also same. So we define function F is 1, 1 in this form. So F of B is equal to F of A implies that A is equal to B. So what is the onto function? So what is the onto function? So F is onto means so G and G dash be the group. So this is a domain, this is a range here. So if we take another element, something F of C here, something elements is there. So this is mapping to this is mapping to this. So this element have pre-image also here. This element have pre-image also. But this element have no pre-images. Therefore, the function F is not onto function. Not onto function. Okay? So function is not onto function. So means every element of G dash have pre-images in G, then the function is said to be onto, but this is not onto. So this is onto function. Okay? Or something C. So this is also onto function. Every element of this have pre-images in G. Okay? So this is the definition of onto function. If the function is homomorphism, 1-to-1 function and onto, then the function is said to be isomorphic function from G to G dash. Okay. And if two groups are G and G dash are the groups here, and F is a isomorphism from G to G dash, then we symbolically denote it as G is isomorphic to G dash here. So this is simply notation for remember. Okay. Then there are so many definitions here. So definition. And onto homomorphism. Onto homomorphism is called epimorphism. So this is just the definition. So there are so many definitions. You know what is the onto function, what is a 1-1 function, what is homomorphism. So you know what are the basic definitions. So we already study the basic definition. Then we define an onto homomorphism is called epimorphism. So what is the next definition? This is definition 1. Okay, what is the definition? 1-1 homomorphism. 1-to-1 homomorphism is called monomorphism. So you remember this definition only here. So what is third definition? A homomorphism from a group to itself, from group G to G, is called an automorphism of G. Okay, what is the next definition? 4. An isomorphism. An isomorphism from a group to itself. An isomorphism from a group G to itself is called, just what happened. So this is this is an automorphism is called automorphism. Okay, so you correct here. So a homomorphism from a group G to itself is called an endomorphism here. So please correct here. Endomorphism. Morphism. So these are the definitions. Okay, definitions. So what is the homogeneous function on isomorphism? Then one in between one and two. Then epimorphism, monomorphism, endomorphism, automorphism. So we take an example. So take example. Okay, example. If G is a group, show that the identity mapping are G to G. So defined by Ix is equal to X for all X belongs to G is a homomorphism. With respect to addition operation. So this is the example. So what is the example here? If G is a group, show that the identity mapping from G to G defined by Ix is equal to X for all X belongs to G is a homomorphism with respect to addition operation. Okay, addition operation. So solution, we know that the mapping I from G to G dash, and this is defined by Ix is equal to X for all X belongs to G. Okay, so this is the definition of identity function. So Ix is equal to X. So if the function identity function apply on X, so we get X itself. So this is the identity mapping. So let X and Y be the elements of G. Then so identity mapping on X plus Y is equal to what? If Ix is equal to X, no, I of X plus Y is X plus Y. But what is this? So this is equal to, so Ix is what? X is equal to Ix. And definition of identity function. So what is Y? Iy. So that is I of X plus Y is equal to Ix plus Iy. So what is the definition of homomorphism? So we define already what is the definition of homomorphism. So that is G into G dash, G and G dash be the groups here with some multiplication operation or it's any operation. We don't know exact operation. So that is star. We give notation star. Star may be multiplication, addition, and so on. So that is f of A into B is equal to f of A into f of B. If this condition is satisfied, then the function f is said to be homomorphism. So in this example, there is a plus operation here, f plus. So that is plus. So f of ab is equal to f of a plus f of b. So for the identity function, we get this. So I of x plus y is equal to ix plus iy. Therefore, I is homomorphism. Homomorphism. So identity function is a homomorphism. Very simple example here for the homomorphism function here. Okay. So we take another example. So let us take example. Let z plus and e plus be the groups of integers and even numbers respectively. Okay, so z and e are the two groups of integers and even number respectively. So define a function f from z to e by fx is equal to 2x, or all x belongs to z. Then prove that, then show that f is isomorphism. Okay, then show that f is isomorphism. Okay, so what is given here? So z and e are the two groups here with respect to plus operation, binary operation. So of the groups of integers, so this is a group of integer and this is a group of even number, and the function is given here from z to e by fx is equal to 2x, so that is even number for integer x. Then show that the function is isomorphism. Solution. So first we prove that. What is the first? We prove that the function is well defined. F is well defined. Well defined. Okay. Suppose x is equal to y. Therefore, x is equal to y implies that what happened? Multiplying 2 to both sides. So that is 2x is equal to 2y. So this implies that this. Okay. So this implies that. What is 2x? 2x is fx. What is it? 2y. 2y is f of y. And if x is equal to y implies that fx is equal to f of y, then f is well defined. Well defined function. Okay, so this is first part here. So then second, we show here this function fx is equal to 2x is a isomorphism. So what is the condition here next? So f is homomorphism. Definition of isomorphism. F is homomorphism. So what is the homomorphism? So consider f of x plus y. So what is f of x plus y is equal to, by definition of this, 2 into bracket x plus y. 2 into bracket x plus y. So that is the 2x plus 2y. So this is what is the 2x? fx. What is 2y? fy. And if f of xy is equal to fx plus fy, therefore f is homomorphism. Okay. So what is the next condition? F is 1, 1. 1 to 1. So what is one-to-one? Suppose fx is equal to f of y, and we show that x is equal to y. So what is fx is equal to f of y? So this implies that fx is what? 2x by definition. What is fy? By definition 2y. So this implies that what happened? 2 get cancelled. X is equal to y. So if fx is equal to f of y implies that x is equal to y, therefore f is 1-to-1. Okay, very simple. So what is fourth? So f is on 2. So what happened for every even integer, for every even integer 2x in this set, have certainly a integer x in Z. So now no doubt for every integer 2x, there exists an integer x, x in Z. Okay, so f is onto. So f is homomorphism, f is 1-to-1, so f is onto, therefore the given function f is isomorphism. So this is a very simple example here. Okay, so we take an example for homomorphism and also isomorphism. So now theorem 1. What is the theorem? So we're taking example. There are simple examples of homomorphism and isomorphism. You can solve many examples on this. So there is a limitation to take examples, more examples. So you can solve the examples from various books. Theorem 1. So what is the theorem 1? If function f from g to g dash is a homomorphism, g to g homomorphism, then one, prove that f of e is equal to e dash. Okay, e dash, where e and e dash are the identity elements. In G and G dash respectively. Okay, so what is second? F of A inverse is equal to FA inverse for all A belongs to G. So if f is a function from G to G dash and the function is homomorphism function, then prove that f of E is equal to E dash is the identity element in G and E dash is the identity element in G dash, and also prove that f of A inverse is equal to FA inverse. So proof. So first part here. Okay, first. So what is given? Let f of G to G dash is a homomorphism function. Let A is an element of G, okay, and E dash are identities in G and G dash respectively, okay, okay. So that is what happened here. So we have E into E is equal to E, no doubt, because E is the identity element, and identity element multiplied by 2 any element is E itself, because G is a group, identity properties exist there. So E is the identity element, E multiply to any element E, So we take A is equal to E here. A is equal to E. So E into E is equal to E here. So we apply. So this is apply the function F. So that is E into E is equal to F of E. So what happened here? So this can be written as, if F is homomorphism, then by definition of homomorphism, so this can be written as F of E into F of E is equal to F of E. So F of E into E is equal to this, since F is homomorphism. Since F is homomorphism. Okay? So then we multiply. So what happened here? So this is what? So F of E into F of E is equal to F of E into E dash something. E dash. Because E dash is an identity element. And E dash is an identity element, and we multiply this element by this. Itself F of E, because E dash is the identity element. Okay? So this implies that what? F of E into E dash. Hence the result 1. Because left cancellation. Since left cancellation. Left cancellation in a group theory. So we already learn about what is the left cancellation, what is the right cancellation. Left cancellation, we get F of E is equal to E dash. Hence the result 1. F of E is equal to E dash. So what is the second result? Second result is what? So we have A into A inverse is equal to E is equal to A inverse into A. So this is a definition of inverse. Inverse, okay? Inverse, okay? So A into A inverse is identity element E is equal to A inverse into A. So we apply the function. So this implies that F of A into A inverse is equal to F of E is equal to F of A inverse into A. Okay? Then what happened? So this is again F is a homomorphism. So what is the definition of homomorphism? F of AB is equal to F of A into F of B. So this can be written as F of A into F of A inverse. Okay? So this is F of E is equal to F of, by definition of homomorphism, F of A inverse into A. So that is F of A inverse into F of A. Okay. So what is the definition of inverse? So in a group, so A and B are the elements of G. Okay. A and B. So B is the inverse of A. Then AB is equal to E is equal to BA. So then we say that B is equal to A inverse. B is equal to A inverse. So A is an element, B is an element of G. Then A into B is equal to E is equal to B into A. Then B is said to be inverse of A. So that is B is equal to A inverse. So this is A something. This is A. This is B. So this is E dash something. E dash. This is F of E is E dash. We prove that. First condition. So this is E. So this is A, B into E dash, B into A. So then by definition. So what is this? What is this? So then F of A inverse. So B is equal to F of A. It's inverse. It's inverse. Hence the condition 2 here. For all A belongs to G. So we prove the theorem. Yeah, okay. So this is very simple theorem. In the next lecture, we also prove some theorems on homomorphism and isomorphism. I am taking examples on homomorphism and isomorphism. Okay, we stop here.